This conference will now be recorded.
Last time we stopped at ResNet. We saw before it how GoogleNet improved the results. So what we had with GoogleNet is that we compute the convolution with different parameters, different kernels, 3 by 3, 1 by 1, 5 by 5, 1 by 1. So we have multiple features that we can find, big features, small features, etc. And it improved the results, as you can see here, and it is also very deep compared to the previous architectures. 22 layers. We had more layers. So GoogleNet came here. GoogleNet came here, and it improved VGG by this by a little bit. And we had versions with a very deeper network. Then this was very interesting. We got ResNet. You can see ResNet here. The improvement was quite big compared to before. So we had a big improvement here from here to here. In percentage, it was huge. Then it's a decent one here and here with VGG, with AlexNet. Then with VGG, we got some good improvements. Then not much here with GoogleNet, but ResNet, in terms of percentage of improvement, was quite big. So what ResNet did, one problem that occurred with very deep neural networks. I don't know if I have I don't have a graph here. Sorry. With very deep neural network, what happened? Normally, in theory, the deeper the network, the better it goes. The error rate goes like that. This is the depth. This is the error. This is the depth of the network, and this is the error. Normally, it goes like that. The deeper it is, the more performant it is. Because the deeper it is, the more complex shape we can learn, the more we can correct the previous shape that we have learned with it's like a layer can act as a correction to the previous layer. So in theory, it's like that. But in practice, it doesn't work like that. In practice, it's something like this. So this is the error. Sorry, it should be here. Oh, let me. So in practice, it was more like this. Error and depth of the network. What do you think this happened? The more we go in depth, at some point, we are here good at the accuracy of the error rate with testing, but at some point it starts getting bad. Why do you think this happened?
Say again, Reba.
What happened in practice? Well, in theory, we can say that the error, this is, the more we go deeper in the network, we build a very deep neural network, the more the error will go down while training. Generally, it works like that, in theory at least. So the more we add layers, layer after layer, the better the networks becomes. But in practice, it doesn't work like that. In practice, we saw that the more we add layers, in the beginning, it starts improving. At some point here, it starts deteriorating. The results become bad. Why do you think that this happened? Why do you think this happened, guys? Tell me.
Overfitting?
It is overfitting probably here a little bit, but it's not really that why we are having this bad result.
It does mean the other layers doesn't have any senses, like.
One of the possible explanations is that the more layer we add, the more what happens to the gradient? What happens to the gradient?
Vanish?
It will vanish. The more we add, the more gradient vanishing we experience. So at some point, we are adding layers, and the first layers, the top layers, are not learning. They are losing information. They are not receiving enough gradient to learn, because it keeps multiplying the gradient, multiplying, and when we reach the end of the first layers, we get no learning. So one very clever idea that the ResNet guys did. Now I think the guy is working for Facebook AI research. This guy, at least one of them. So you can see here, it's very deep for ResNet. What they did, very simple and very like clever trick. Instead of like doing a direct connection, they will just they keep the direct connection layer after layer, the different conv layers, but they connect this here. They just do an addition. They did a connection here. So here we have this output plus this output from here. So what happens when the gradient starts flowing to update the weights? So we get the regular gradient here that comes here, and the gradient here. This one is always better, this gradient here, because it travels less. The gradient that comes from here travels less.
Yeah.
So which means that this, at least if this one is not sending a lot of gradient, this one will send some of the gradient. So these layers will receive some of the gradient. So this residual connections is just, we do a sum. We have an output here, some feature maps here coming out of here, and we sum it up with the feature maps that came from here. And we keep doing that. It's just we connect the previous layer. It's like we do a jump connection, a short circuit if you prefer. So that way we have some of the gradient flowing through here. Does it make sense for you guys? What do you have to say about it? Tell me, guys, please.
Can you repeat it, please?
Yes. Did you understand this bit, this problem, these two graphs that I just drew?
Yes.
And Yusuf, did you understand this?
No, this one, no. The practice
Okay.
one, not
Yes.
this one. No.
This one, yeah, okay. So in theory, the more layers we add, like in here, the more my neural network, my convolutional network becomes performant. Does it make sense for you?
Yes, yeah.
Yeah, the more we add, the more performant my neural network becomes. So normally, this is the depth. The more layers we add, normally this is the error. The lower the error becomes.
Okay, yeah.
At least in theory, but in practice it doesn't happen like that. In practice, it happens like that. We are adding layers, adding. Things are improving. At some point here, things are deteriorating. We are not improving anything. This is odd. This is not normal, because on every layer should like improve the previous layer before it. It is odd. Do you agree with this, Yusuf?
I have a question.
Yeah.
Yeah.
Is there in TensorFlow, for example, in the basic example that I said, we fix the iteration at 300. Is there a method to say stop when the accuracy is best?
Yes, early stopping.
Yeah. Is there
early stopping?
like
but
that?
This is really, it's not really related to this. It's not.
Yeah,
it's not
but
the iterations here. It's the depth of the network. This is the depth. How many layers we have. It's not the number of iterations.
I just want to know if there is something in TensorFlow is to say stop when the accuracy is the best, I would say.
Yeah. You can implement an early stopping.
Okay.
You can use early stopping for this, yeah. So it's a separate question. That's fine. So you understood this problem. Yusuf, did you understand this problem?
Not, to be honest, not clear yet.
You understand what is the depth here, the D?
Yes, okay. Yes, you said that each time we add the layer, theoretically it is more accurately.
Normally, it should be more accurate because each layer improves what we learned in the previous layer.
Yes.
At least in theory. But in practice,
why in practice doesn't?
Yeah, in practice it doesn't. But you understand that this happens in practice. What's the difference between theory and practice here?
Yes. Okay. Yeah.
Yeah. One of the possible explanations is because of the vanishing gradient. The more we add, the layers that we add, the gradient will, so for example, we compute the error, the gradient will flow backward, and we start updating the network. We start updating the weights. Do you agree with this? That we are updating the weights based on the gradient?
All right. Okay.
If the network is too deep, what happens with the gradient is that we multiply the gradient. If you remember how we did backpropagation, the gradients get multiplied until the end. And normally they are between 0 and 1, normal in general. So if we keep multiplying numbers that are between 0 and 1, what happens at the end? So if we keep multiplying them, they will become smaller. Yes, Yusuf?
No, not clear.
Well, it's a simple mathematics.
Yes.
0.1 multiplied by 0.1 multiplied. What does it equal?
Okay, yeah, it gives you a smaller.
A lot of zeros. One. That's simple mathematics. So when the gradient flows backward, it gets multiplied at each level. The local gradient multiplied by the previous gradient, and it keeps getting multiplied. So at some point, there is a limit to the precision a computer can work with. So if you have 32 bits, we always have a limit. We cannot represent an infinite number of zeros.
Yes.
So and at some point, it just becomes 0. It means these layers, for example here, may not learn anything. They don't get updated. They are not getting any update. Or they are very slow at learning. So this is the problem.
This is like CPU issues.
Yeah, the limitations of the memory, of the RAM, because nothing is infinite. There is no way we can have an infinite memory representation.
Yes, yeah.
So what ResNet did, what the guys did, is to add connections. So instead of stacking networks like that, so this, for example, these 2 layers are here. They have their output, their feature maps, the shapes that they learn, and we add to them the previous output. The previous one is added to them. Here. Same here. And when the gradient will flow backward, what happens? The gradient will flow in this way and this way, in both directions. It has to flow backward like this and this. And this gradient here, is shorter. It will take a shorter path. Yes or no? Compared to the gradient that flows into this direction. This one is shorter. It is half the distance. Yusuf, do you agree with this?
Now, can you repeat this?
When we start learning, we have the gradient that will flow backward. So we have a gradient that flows in these directions, and the gradient that will flow towards this direction. So this gradient that jumps in here will travel a shorter distance than this gradient, because this will travel like 2 layers. This one will travel will jump here.
Yes, yeah. Quicker.
It's quicker. And then this one will jump here, this gradient. So we have at least a portion of the gradient that is traveling less direction, less distance. It is traveling less than this. So here the vanishing gradient will happen less. And these layers will learn more. This is a very simple explanation to what is happening in the ResNet. So it's like having another path. The gradient can travel to a long path and a short path. If the long path doesn't work well, the short path can compensate. Does it make sense? Guys, does it make sense for you? Please. No?
Sorry?
Does it make sense for you? Do you accept this explanation?
Yes.
How do you feel about it? Sorry, what did you say, Miriam?
Yeah, that's okay.
Perfect. Yusuf, are you happy? All of you guys.
Yeah, it's somehow clear, not 100%.
Yeah. But that's fine. Like we have like two gradients, two paths for the gradients. One that is a bit more precise but long, and it can lose information, and one that is shorter. Travel
Yeah,
less,
this is clear. Yes.
yeah. So that's all what I wanted to understand for this.
But couldn't we like keep like the minimum layers? Don't add more.
But that's a good question. But we will like reduce the accuracy that we can reach.
Okay.
We will not be able like to go to a layer that big, 152. And this one is what improved the results here. Small layers like this one, VGG, that we have seen last time.
Yeah.
Got this accuracy or this error rate, 7.3. And here we got 3.6 because we were able to go very deep. 152 layers. And this architecture won most competitions in ILS VRC and COCO. COCO is for localization. Does it make sense for you guys? Are you happy with this? How we could, it's just a trick, just a sum. We sum, we have X and we have Fx that comes out of here, and we sum them up. So we have like the two feature maps that are here, and we make the sum. It's so simple, but the results are very good.
Aridam.
Mm-hmm.
I thought the ResNet would solve both like vanishing and exploding gradients.
Yes, but both are of the same problem, vanishing and exploding. They have
Yeah,
the same
because
nature.
you were saying only vanishing. So
Well,
yeah,
because it occurs more with because we have regularization and we prevent the different weights to go very high. So what happens more when we stack more layers is the vanishing, because our weights are generally small. That's all. But they both, it deals with both, with vanishing.
Okay, yeah.
Thank you for this. Now, are you happy with ResNet?
Yes.
Such big layers. Now let's see how we can compute the memory and the RAM and the number of parameters for a neural network, a convolutional neural network. Let's take the example of VGG. This is the input. The input doesn't have any parameters. It's just an image. So this is the size of a VGG image, 22 by 224 by 224, which is how big the image is. 3 is the number of channels. So it contains like 150K. So each image contains 150,000 number, float or real if you prefer. We are not counting the bytes just for the sake of simplicity. Then convolution 3, this one. It's 3 by 3. the first convolution, 64 channels. So yeah. So this one produces, well, it uses 3 by 3, the kernel of 3 by 3. So it's scan the image on 3 by 3, and it has 64. It produces 64 here filters or feature maps. So how many, with a kernel like this, how many parameters do we have? 3 by 3, how many channels do we have? So the image is 224 by 224. And how many channels does it have? Unmute yourself, please, and tell me.
3.
How many?
3.
3, yeah, RGB. So here is our neuron. It is 3 by 3, so it takes a zone of 3 and swipes through the image. It convolve. Convolve means it swipes through the image. So how many parameters my neurons have? My neuron have. This neuron that use 3 by 3 kernel, how many parameters does it have?
10.
9.
Why 10?
10. Yes.
Not
It's
really.
not 9 add 1.
It's 3 by 3.
Yeah.
By
9.
3. Don't forget the channels.
Oh, yeah.
So the input is 3 by 3 here, but the channels as well. So it's 3 by 3 by 3.
27.
For one neuron. Normally plus 1 for the bias. So how many neurons do we have? How many neurons do we have here? We said 64 feature maps.
28.
So we have 64 neurons because we can learn 64 different shapes. So it's 28 by 64.
Yeah.
How much is this? Can you tell me, guys?
1,792.
And 92. Here it's because without the bias. Here from the source, they didn't count the bias just for the sake of simplicity. So this is the number of parameters. But the memory is not just the number of parameters. It's the number of parameters and the whole feature map that we are producing. This is the biggest problem. The feature map will be stored in memory. You agree with me? So to know the parameters is to know the speed more or less, but the feature maps tells me how much memory do we need. So to compute the size of the memory is just we compute 64 multiplied by this distance. If we're not using padding, it's 224 by 224 because they are. If we are using padding, this one and this one will be the same. So it's 224 by 224, the image and the feature map, but here by 64. So it is 3.2 megs. Did you understand how we come up with this number?
Yes.
Yusuf, you are courageous to tell me no. Amal, you wanted to say something?
Sorry, I was just not focused. Trying to.
Oh, no problem. No problem. Now here we want to compute how much RAM do we need? How much memory do we need? So we have the number of parameters, this one. But to compute how much RAM do we need to store this feature map, we need to compute it. So this feature map is generally the length and the height are the same as the image. If you use padding normally, this one will have the same length, height and width. So it will be 224 by 224. But it will have more channels, 64. So this is just the size for this. It's 224 by 224 by 64. Is this. So this is the output of the layer, of this first layer. That's the output of it. That's its output. Okay? Are you happy,
Yes.
Amal?
Yeah,
So
yeah.
this is just the output. So
Mhm.
it is 3.2 megs plus this. Well, this is a lot bigger than this. Million, sorry. The 3.2 million parameters, not
Yeah.
mega, because I have to multiply by 4 or depending on what's the size of a number. And same goes here. Here we didn't use a pooling or anything, so it's the same size. So just this, and then we have the pooling layer. The pooling layer will reduce this size. So it will divide it by 2 here and by 2 here. So it's just, it divides it by 4. It will be 800,000. A pooling layer doesn't have any parameter. It just, we take the maximum out of every pair of, out of every 4 numbers. Is it fine? Yusuf, tell me please, tell me no.
I got lost.
No problem. At what point? At what point were you lost?
The channels.
What channels? The 64?
Yes, yes.
So yeah, this is the number of channels for this layer. We picked it for, we choose it to be 64. So we are computing 64 different shapes in the first layer. So we have 64 neurons. So we are producing a feature map that is 224 by 224. It's the same size as the image, but with 64 depth, a depth of 64. That's all.
When you say producing, do you mean that's the outputs?
The output of this layer, yeah.
Yes.
This layer is just 64 neurons. Each neuron will produce like a feature map, an activation map, by swiping through the image. Each neuron will swipe. So each neuron has just 27 or 28 parameters, but because it swipes, it will produce a lot more numbers.
Okay.
It's swiping through the image and producing a number. Each possible swipe, like it convolves and produces a number. So this one layer here, just one layer in this cube, will be the output of one neuron.
Okay, yes.
And so we have like 64 here. Like layers, 64 matrices stacked here. So this is the size of this output. So it is 3.2 million outputs. 3.2 million here as well. And then we do the same thing again. 1.6 million here because the pooling layer has reduced the things. Pooling layer divide my matrix, this one, by 4. But because it takes out of every 4 numbers, it takes the maximum and remove the others. So this cube will be a fourth of this after the pooling layer. Is it fine?
Yeah, yes, fine now, yes.
Perfect. You guys, are you happy with this?
Yes, yeah, thank you.
Perfect. So here it is reducing. Then we get more because we have a bigger number of features. We have 128. It is bigger, so it goes bigger. Then another pooling. It goes smaller. You can see the pooling helps a lot to maintain the RAM.
Yes.
Then when we go here, the memory for the fully convolutional layer is very small, as you can see. The number of outputs, it's because we are not swiping for, like, it's one neuron is connected to the whole image and produce one number. So we are not like swiping through the image and producing multiple numbers. It's like we take everything, not the image actually, this feature and this activation map. We take in all of it and producing one number for each neuron. So we have less parameters, less memory, sorry. But the number of parameters is just insane here. It's because if we have something like that, every neuron that we have, so here at this output, we have this activation map, 5 here, where is it? Yeah. At here, we have 7 by 7 by, it's very small, as you can see. by the successive pooling layers, we've got just 7 by 7. So here we have 7. Here we have also 7. But here we have a long one because we need to learn many different types of shapes by the end here. So the complex shapes, we have more of them. So it is 512. And when we put a neuron here, if it is connected to everything, not just like in here by 3 by 3, it means it has how many weights for every neuron? 512 by 7 by 7. This is the number of weights because it's connected to everything. So it produces less output. Every neuron will produce only one output instead of like here it produces a lot more. It produces only one, but the number of weights that it has is much bigger. 7 by 7 by 512. And the number of neurons are 4,000, over 4,000. So we multiply them to get the total number of weights here in this layer. So we get 10 million here.
Excuse me, the last 3 layers, what are they?
Fully connected layers. It's regular neural networks, not convolutional neural networks.
Okay, with for example, with a sigmoid or something like that.
Yeah, we always use a sigmoid generally after that.
Okay.
Put a sigmoid here and everything, and like this. So this every neuron here is connected to the whole tensor here. This cube is all connected to the whole, or this cube here is connected, or like all of its data will be connected to this neuron. Unlike the convolutional neuron, it is connected only to a small portion at a time, and it wipes. So it produces more outputs, but it has less weights. Here is the opposite. It produces only one output, but it has a lot more weights.
Okay.
So you can see, guys, that the number of weights are higher at the end. Here, at the convolutional, at the fully connected layer, we have more weights here. But the RAM is a lot here. We have more RAM required here, as you can see. But not that many weights, 1,000, 360,000. But here we have a lot more weights. Okay, so if you want to optimize like the speed, you need to like not use a lot of like neurons here. Otherwise, it will take a lot of time to compute all the gradients. But if your GPU is limited in memory, you should, for example, shrink your image. And this is a very small image, by the way, 224 by 224. It's a very small image. Now, with regular cameras, we have a lot more. 8,000 by 8,000 is normal nowadays. But for classification, when you shrink it to this dimension, it's fine. So here we are computing how many RAM do we need for this. It's 24, and if we 24 million. So if we look at this, this is like just how much every parameters need. If it is a float, a regular real number, we need 96 million per image of memory here. So for every image, we are, well, we don't need to store them all at the same time. But to compute this, for each image, we need 96 megabytes per image. And of course, we are going to store different images inside. We do a lot of things together, and we compute this in parallel. We try to compute them all in parallel. So for each batch, we need to do this computation in parallel. And we get the results like all in parallel to be very fast and compute then the error. So that's why your batch size will limit how many images you can use. So if you make it like 100 megs, say per image we need. And if you have, for example, 32 images per batch, so it's just like you are almost at 4 gigs. That's huge. That's just for batches of 32, guys. It's just insane how much RAM it needs. And 32 is really nothing. It's really actually a bad batch size. What do you have something to say here?
Well, you said that we could run the batch in parallel.
Of course, batches are generally run in parallel. When you send them through the network, because
we know that each batch will require the recalculation of the SGD, the gradient.
Yes, so that's why we process one batch in parallel, 32 or something, all in parallel, get the output, all the outputs at once.
Yeah. So the gradient, how will be recalculated in parallel?
How you get all the errors in parallel. So the gradient is based on the loss function and the back propagation. So once you have the loss function, you start doing the back propagation.
Yeah, but you said that the batch are executed in parallel. So you execute.
Yes.
We know that each batch will recalculate the gradient with back propagation. You agree?
Sorry, not all the batches in parallel. It's impossible to compute all the batches in parallel. I mean, the images inside one batch are computed in parallel. All the images in one batch.
Oh, yeah.
The 32 images, if you will. So they are all processed in parallel.
Okay.
So this is how. But again, guys, this is for a required for a forward pass only. Around 100 megs is only for a forward pass. When we do back propagation, we need 2 to 3 times the amount of RAM required. So that's really big for ResNet. The amount of RAM required is really huge. So for example, if we have a batch size of 32, without counting the forward, like the back propagation, we need 3.2 gigs to do it. That's why in the example I sent you before, I used only a batch size of 20. So that was the only thing that could work, the maximum that could work on my GPU. My GPU is just 4 gigs. What do you have something to say, guys? Can you see now how much RAM do we need? How much weights? How to compute the number of weights? You are too silent. I'm worried.
Yeah, that's okay.
That's okay for you guys. Perfect. Amal, Najwa, Yusuf, the other Miriam.
Yeah, I think it's fine. Yeah.
Farouk, Ratiba. It's fine how to compute and how much you need. How much memory do you need?
Yes.
So it's 200 megs per image in the ResNet, actually, almost like something like that. We're on the thing. Perfect.
How important is this?
You don't need to do it, but you can estimate, because otherwise you will always fall in the problem of OOM, like out of memory error. So you don't really need to do it, but it's good to have an estimation. And in interviews, it works very well. Yeah.
Only now I understand how memory works with the GPU, with the consuming space.
Yeah, how much memory it needs.
Yeah.
It's just insane.
Only now I see the efficiency of memory and the models of deep learning.
Exactly, yeah. So you need like 200 megs per image. A small image, which is just insane. A small image that small requires 200 megs. So yeah, in a batch like that of 32, you probably need something like at least 7 gigs, something like that.
So for general guns models, so we need the huge memory, isn't it?
Of course. Of course, you have a generative model is also very deep. Can be very deep, and it has 2 parts, 2 networks. We will try to do it next time. So it has like two networks. There's not only one, and they need to be both trained at the same time, or not really trained at the same time. Sorry, one needs to be trained and still loaded in memory. So you are happy how we are computing? How much RAM do we need? For
Yes.
yeah, perfect. Now what do we have? So yeah, this is what we are talking about. Now we are going to talk about some problems. This is somewhat funny. So this is something that happened at the University of Washington. A group of researchers trained the CNN to recognize wolves and huskies. Can you make a difference between them? Najwa can probably.
No.
I can't. I can't. I have no chance like of succeeding. The thing
They're
is,
wolves.
well, I don't know. I have no idea what's the difference between a wolf and a
It's
husky.
like wolves and huskies.
Yeah, well, some of them are wolves and some of them are huskies. But yeah, it's very hard to know which one is what. But they got a model. They produced a model with an accuracy of 90%, probably better than experts by a big margin. So despite the distinct, this is something very hard, distinguishing between them. So what happened? One thing that happened is that most wolves' images contain snow. Most images that had wolves, like this one, had snow next to them. And most images that had huskies didn't have snow. What do you think happened?
They detect only snow.
Yeah, the model, because the model we can't control it. We don't have control over the model. It converges by itself. We try to find the best way, some between quotes, somewhat the best way to find to discriminate between the images, the classes. But they ended up in reality to build a snow detector, because every image that contained the wolf had almost had snow, and other images that didn't have wolves didn't have snow. So the model will probably look for snow. That's all what it did. It's like asking a baby to make the difference between things, and it will automatically go to the simplest thing to make the difference. And they managed like a 90% accuracy with this, which is funny.
Yeah.
Yeah. So what do we do? One of the ways to detect how the model is doing is to use explainable artificial intelligence methods. What it does, it tries to find what are the pixels that influence the decision. It removes some like a portion of the image, like Lime. Lime is like a framework that can remove portions of the image and see if it has influenced the decision. So in that case, if we apply it, we will Lime will highlight that it is snow, for example, in this image that made that influenced most of the decision. So when we remove it, when we remove the snow from the image, we put it black, the thing will be detected as a husky. And when we keep it, it will be detected as a wolf. So this method, it removes portion of the image and send it to the classifier and see what portion is influencing the decision most. So this is one way of doing it. Other problems with neural networks, adversarial attacks. So for example, we have a panda here in this image. We apply the small noise to it, multiplied by 0.007. So this is the product. So this is a very small like noise applied to it because it's multiplied by 0.007. And we get, you can barely see the difference, guys, between this image and this image.
Yeah, it's practically the same.
Yeah, this was recognized as a panda, 57% confidence. This was recognized as a gibbon. This is another animal, completely different animal, with a 99.3% confidence. Why do you think that this happened? Why do you think this happened? Tell me, guys. What's the reason? What happened in here?
The
model,
there's no clear reason, to be honest.
Okay, yeah.
Maybe through the layer, the node, like it's multiplying, so it gets bigger and bigger.
No, it's 0.007. You can see the image has barely changed.
Yes.
Wanted to say something, guys?
Maybe it's the model is too general.
It's probably the opposite. It's not too general. It's because the model is trained on a particular probabilistic distribution. Most images that came to the model don't have this kind of noise applied to them. Can you hear me, guys?
Yes.
Yeah.
Yeah.
So most.
But why the neuron make a relationship between the noise and the given?
Yes, because now the noise has created some features that were used for the given, even if it is random features. But this neural network, this model, has never seen like images that has a particular distribution, certain images with a particular distribution. Like, for example, most images are taken by a number of cameras, not by every possible camera in the world. And these cameras have specifications. Maybe they were taken in a direct sunlight, for example, this during the day. So certain images that can contain a panda may come from a completely different distribution, where this kind of noise didn't exist in them. Because like noise is present everywhere. We just don't notice it because in our mind we have models that are super general. The generalization of humans is just impressive. How we can like generalize over things that when recognizing. But these images come from like a completely different distribution as like compared to this one. And when we give an image like that the model like is completely alien to the model. Even in testing, even test images don't come from the same distribution as in here that has this kind of noise, this kind of configuration. It never appeared. So the model, what happened was fooled. It was just fooled because it has never seen something that has this kind of noise before. Even in testing as well doesn't have this kind of noise. It's very rare to have it. So the model doesn't like focus in the global image, but because it starts building things at the micro level and then building the features. So this kind of noise can create totally different features that were used, for example, for gibbon and not for panda. And the model was just full. Yeah?
I have a question. If we apply different filters at the beginning, you see the filter that allow us to keep only the shape, the antiristic shape. Does this could fix this problem?
Probably not. In this case of problems, because the problem is from the data itself.
From?
The problem is in the data. The data don't have this kind of noise. Maybe this pattern exists for.
Yeah, but if I apply the filter on this noise,
a filter is just a neuron. A filter is just a neuron that is detecting some patterns.
I'm not talking about the filter of neuron. I'm talking about filter on image.
Yeah, but you have to target. Okay, now I got you. You have to know what filter to use.
Yeah, I apply filter on the image to keep just the antiristic.
You can't do that, but you have to know what filter to use because this is called an adversarial attack. It means that an optimization process was run to find the noise that will create these problems. You can imagine if you have a driverless car and you can create a noise by a reflection or something that can create a problem and then you can have an accident. That can be very dangerous with these adversarial attacks. But yeah, you can use a filter, but you don't know what filter you need to use. You don't know like all the limitations of your model. You need really to explore all of them, all these limitations, and try to find the right filters to use. But the filter, yeah, can probably have some effect here. So you got what happened in this case, guys. It's because we are leaving the network to learn by itself. The model is learning by itself. It is possibly learning some features that are in the data but are not super general when we go to the outside world, where we have like cases from every probabilistic distribution. So maybe a gibbon has some features that are in here, mixed with here. And yeah, the network has learned that a gibbon has this kind of features mixed with here because of the probabilistic distribution of what the gibbons come from, the image that is generated or taken for gibbons. And this has led the network to make some serious mistakes like this. 99.3. Yeah.
Sorry. So are we expecting exactly that we have like given with like high confidence, or is it did it come as a surprise? So is it like expected?
No, I don't think it was expected by the authors. They expected that there should be some problems when we look at the neural network, because it's not by itself. It has looked only at the data that we use for training. It's not like humans that we have looked at different cases, different areas. Like we have seen a lot of data, more like even beyond this images. So maybe it wasn't fully expected, but they would have expected some errors. But this one was like a big error. Like to put just some noise and get gibbon was probably not something that is expected at 99% confidence. But errors were always expected, but maybe not this kind of error. Does it answer your question, Emil?
Yes, yeah. I have another question. So, I mean, what's the limit of this model? Like, can this like go beyond human intelligence, or?
Yeah, not fully, I would say, because we are much better at generalization. But you have to make sure that in testing or when you deploy your model, the images that are coming they don't come from a different probabilistic distribution. For example, they are taken in a completely different climate or different engines or different tools. This kind of things. You have to make sure that the difference in how or the settings or for where the image was taken is not too different. Otherwise, you need really to explore your model more and see if it is really general enough beyond not even beyond the training data, but beyond the probabilistic distribution. Probabilistic distribution means like the basic structure of your images, the hyperparameters of the images. For example, the photograph tool that you use to take the photos is not like too different between the different cases where you are using your cameras. So this is like even the hyperparameters of how the data was acquired, not just the data itself, how the data was really acquired, how the images were captured. Okay?
Yes.
Yeah, it's
so. Yusuf, are you happy?
Yes, yeah.
Yeah, but with this kind of errors that, yeah, external parameters of the cameras, etc., can influence things a lot, like in here. But humans, generally, they don't do this kind of mistakes. We are much better at generalization. So that's why, like, putting a driverless cars model and this kind of things can be very tricky. It has really to be like general to the maximum. Another adversarial
Areda, sorry, I have another question. So, so does it work with supervised or unsupervised learning or both?
This is more of a supervised thing. For the unsupervised learning with images, it's because we don't even look for labels for the supervised. But there we can find the probabilistic distribution of this. For example, if we use that would be an interesting topic to talk about next time with what I'm thinking of, with autoencoders, etc. sometimes you can detect if your image comes from the same probabilistic distribution as your data set with autoencoders or with PCA. You can find if they come from the same area or not. But let's discuss it next time. This can take some time to elaborate.
Okay, thank you.
So now another adversarial attack, a washer, by adding just some noise, I think here. Here we got, it was, it's barely different. Nothing, you can't see the difference. Maybe they added just some noise here, and it was like a safe at 34%, a washer at 22%. And then this is another type of noise. This like became a safe. Like you can see some type of noise, a little bit of noise, like made the model confused between a safe and a washer, a washing machine or dishwasher, whatever this is. You can see that. Like because when we add the noise, this type of noise never occurred in the images. So it really makes things confused. So this is the parameter of the noise. Another adversarial attack. So say this image was recognized fine, stop image. Then we added only a sticker to it, some stickers. It was recognized as a 45 mile per hour limit. There is no 45 here. It's because this image, this type of image where we have stickers, they never occur. It's alien to them, completely alien to the model. Like images with stickers, they don't exist. So for the model, it just makes it confused, and it will just try to find some features that can get it to the closest class, and we get this bad classification. So you can see that if the image comes from completely different distribution, where these patterns like never occur in the training, we can really end up with bad situations.
So how did I solve it? You should give all the different pictures that they exist.
Yeah, it's still a research area. They will try to find different attacks, for example, adversarial attacks, a lot of them, and see how the model is performing. So it's like a very deep evaluation when we want to take the model to the outside world. If, for example, we are in a supply chain and we are producing some parts, say, and the settings, they never change. When you take the photograph of the part, for example, like a tool you are producing, like screws, you take a photograph and you try to see if there are defects on them or not. If the camera doesn't change, the lighting doesn't change, there is no problem. You can use it easily.
Okay.
But if you go, for example, for driverless cars, where things you don't control the environment, or I don't know, if we take, for example, a scan chest, it's not too bad because we can control the environment. But in this case of driverless cars, we have to evaluate the model very, very deeply. And we try to do these adversarial attacks a lot and see how the model is performing. If it's not doing well, we have to change things to add add more data, to apply these patches more and do the data augmentation. It's like we create new images based on these minimal adversarial attacks and feed them in the model to make sure the model is doing well and keep doing. You can see that like real life problems where we don't control the environment can be a lot more difficult.
Yeah.
Yeah, but this is gonna be like endless issues, endless data coming.
It could be, yeah. You have to evaluate it. That's crazy, yeah. That's true.
I mean, like, if that car, you drive it, I don't know, let's say in London, and then you move that car to another city,
yeah.
it's a whole different. So you cannot, it will restrain the utility of that product if you can use it.
Yeah, exactly, yeah. That's why for this kind of models, like the evaluation takes a lot more time than training, because you need to keep always evaluating it in different scenarios, different cases, even generating new ones by yourself, simulating them can be just a lot of work. Is that fine?
Yes.
Perfect. So I will give you a pause then. And after this, we will do semantic segmentation. So let's
Nice.
take a 10 minutes pause, and we go back to semantic segmentation.
Okay.
This conference will now be recorded.
So semantic segmentation. So this is, in the first image, it's just a categorization. We determined what is in this image. It's one single label. This is what we used to do so far. Determine what do we have here. With semantic segmentation, we try to determine in our classes what are the pixels that constitute them. It's harder. So we don't say only cat. We also tell what pixels constitute my cat. So we draw it like. We have grass here. We tell what pixels constitute the grass, the trees, and the sky. And we put them together. The pixels that represent the same thing. So this is what we mean by semantic segmentation. It's like we determine what pixels are related to what. So we classify every pixel. Every pixel is classified. So we determine a class not only for the whole image, but for every pixel. Each pixel gets its class. So how would you do that? Give me your solution. How would you classify every pixel by itself?
Maybe shape.
Maybe what?
Shape.
Shade.
Shape. Shape.
Well, so some pixels, some a cat has this shape. It can be a completely different shape. How do you classify every pixel? Using machine learning, like or convolutional neural network or regular neural networks. You want to classify every pixel. So this is cat, etc. This is tree, all of them. So we produce a matrix of classes, something like that. But not it's just a 2D matrix. It's a 2D matrix like this. And in each cell, we have what class it is. So each cell represents a pixel and what class it is. We don't have like depth, no channels, because it's just classes. So how do you do it, guys?
I believe that we during the training we add a dimension for our data. Before it were 3 by 3 by the number of colors RGB. Here we add another dimension to specify each pixel what it is at the beginning. No.
Well, the pixels or the data are annotated. You have the image, and you have like a matrix for every image, telling you what pixel it is in every one of them. So the data is annotated. There's no problem with this. But what kind of network do we use to classify every pixel?
Convolutional? No.
But how will it end? How will it be at the end, or at the beginning, or how do we? Convolutional network will produce classes for the whole image. So how do we do it? And we can't take every pixel individually and know what it is. A pixel in itself doesn't mean a lot. A white pixel or a black pixel. A white pixel can be the sky, it can be the cat.
Segmentation, Rera?
How?
Segmentation.
You mean you use segmentation algorithms like
Yeah.
classical ones? You can do that. You can still do that, but it's not. They won't be super performant. So you segment things and you try to classify them individually, and you see what it is. This is one way, yeah. But with neural network, can we do it? Can we do it with neural networks? One way of doing
object detection?
It's like you reverse the problem. You do object detection, but object detection will just tell you the bounding box. Just tell you this zone has a cat. but it doesn't tell you exactly what pixels. Okay. So this is one way. I want you to focus here, guys. We are going to finish in like 10 minutes, not worry. So this is, we have a picture here of a cow or 2 cows, and we want to segment them to determine how many cows or the pixels of the cows that we have. So we can build the convolutional neural networks. Normal, a regular one, many conv layers. And the last one, what kind of shapes this one is going to detect? What kind of shapes this one is going to detect?
Really small shapes.
Perfect. And this one?
Bigger one, more complex one.
And this one?
Connected one.
Probably a lot more complex. Maybe the heads,
yeah,
the feet, etc. here. And in each, what we will have in every layer here of the activation map? What do we have here? So this one could be what? This layer.
A head, but in different position. A head in the top, head in the left, head in the bottom.
Where do we have a head, for example? Good. It will tell me where do we have heads with a certain degree. It gives me a number. What is close? Where do we have something close to a head? Here it could be something like feet. Here it
maybe the whole body of the cow, no?
It could be. It's possible. Yeah. This could be the grass. So we can take the maximum. So if we take this is for one region of the image, 1 pixel, if we say. And we have values here, different values. So for example, this is, let's say this is for head, this is for feet, second one is for feet, third one is for sky, and the fourth one is for grass. So if we have here 1, here 0, here 10, and here 1 as well. So this is probably what? Here we have 1, 0, 10, 1. What does it mean for you? What does this mean? Don't be afraid of speaking.
Sorry, Reda, what do you mean by these numbers? Are they weights or what's it?
Yeah,
there
the
is
output
no
of a network, what they are? They are similarity measures, the output of a convolutional layer. So we got similarity measures. If it is very close to what we are learning to here, it will be a high number. If it is not close to it, it will be a 0 or a low number. If you remember.
The second feature there doesn't exist. Second feature.
Yeah, it probably doesn't exist in this pixel. Probably not it, or next to it. So it means this pixel is probably what? Sky. It's very high. It's very close. The shape. Yeah, the shape around it is very close to a sky.
But you said that the input are labeled. I see the input.
They are labeled, yeah, but we are not looking at the label yet. The labels are when we compute the loss and we try to update.
Yeah, but what I can't understand is that in the input I see 3 per H by WI. So I don't see in entry data we don't specify for each pixel, is it a sky or is it a cow or is it
well, when you have the network trained, you don't know when you try this image, you don't know what it is because it's a new image.
Okay, so we don't say in the input we don't have if each pixel is it a sky or
for the training data we have that. For the training data we have that.
But I don't see it in the input.
You don't see it here. You are not going to see it here. You are going to see it out after the loss. Is the loss function when we get the output. We put it in the loss, and here in the loss we have everything. We never input, even in the examples that you did, you never put the labels in the input. The labels were separate from the input. It's the loss function that uses the labels to improve the network, to train the weights. We don't input the labels. They are not. They don't go inside.
Okay.
They are used to just to train.
Okay, but we must say to the network that this is a cow, this is a sky, this is a chicken.
Yes,
this
but
is a
not
green.
here, not in the network. In the loss function will do that. The network has no clue what sky means, or it will just optimize to find this as a sky here. But it's the loss function and gradient descent that will look at the output. If the output look like the labels, it's fine. If it is not, it tries to improve it by modifying the weights of the network. So if we put the labels inside the network, then our data that will come in testing or that will come later will need to be labeled, which is not normal. Data that will come in the future are unlabeled, and we need to predict things for them. So here we have to always have something that is unlabeled. Okay. Maybe Nassim, I will send you the course where we did.
Here the target is the image that are in the right.
But the target doesn't go in the network. We never put the target in the network.
Okay.
Otherwise, when examples are coming in the real world, we need the targets. But the goal of the network is to predict the target.
Yeah. But what is the target here? It's an image plus label. Exactly.
It's an image plus a matrix. In this case, a matrix that contains for each pixel what it is.
Yeah, that's fine. That I understand. Mm-hmm. Okay.
Okay. So guys, what is this? If we take this row here, what does it mean? Tell me, please. What does it mean? Yusuf, tell me.
No clue, to be honest.
What every layer means here?
It means he detects one of the shape with the certain
every
probability.
layer is related to one particular shape.
Feature.
Yeah, every layer is related to one particular feature. Do you agree with me, Yusuf?
Yes. Yeah. Yeah. I got this. Yeah.
Yeah. So
what does
this mean here? When it is a high number, if you remember, it means that it is very close to the shape. When it is a low number, like 0, it means it is very far from it. Doesn't look like it. Okay?
Yeah.
So when it is a 0 here, it means that this pixel that is in here is very far from feet. It doesn't belong to feet.
Yes.
It is somewhat close to a head, somewhat close to grass, and very close to sky. So what we are doing here, argmax, we are taking the maximum. We produce a matrix. We don't even need the fully connected layer here. We take the maximum in everyone. Argmax, it means a position. So here, what position is the maximum? 0, 1, 2.
11.
11. What 11? What position 10, is the maximum? 10. No. But 10. What position?
Third
position.
Third one, or 2 if we start with 0. Normally we always start with 0. So it is 2. It means class 2 here, and so on. So we give the class that is the position at what maximum. Argmax means the position of the maximum. So 2, it means the third layer. 0, 1, 2. This is the third layer, which is sky. And we do the same thing. So we get for every pixel its class, based because every layer is able to determine what class is or what pixel or what is the shape of the pixel or the other pixels around it, because a pixel in its own
Like,
doesn't mean a lot.
Rida, like the higher probability?
Yeah, these are kind of not really probabilities, but yeah, distance measures. It's the distance. The higher it is, the closest it is to the shape that we are looking for.
The Rida, there is a like a membership function here. A membership function.
It is the work of the convolution. The convolution is a neuron that gets some input. A neuron, when it gets some inputs, it has some weights. It multiplies them plus this multiplied by a weight plus this multiplied by a weight, and so on. Is this fine?
Yeah.
This is exactly what we call by dot product. The dot product of two vectors, f by s. We multiply every component of the vector and we do the sum in the dot product. If you remember it from high school, the dot product.
Yes.
When we multiply two vectors, we just multiply their values and sum them up. Or it is equal to what again? F, the length of f by s. These are two vectors like that. F multiplied by s multiplied by what, if you remember? The dot product between these two vectors. The length of f, this is f, this is s. The length of f multiplied by the length of s multiplied by what?
Cosinus?
Perfect. Thank you, Najwa. Cosine of alpha. This is really from high school, maybe even before. Scalar. It is what we call also the scalar product. The dot product is also the scalar product.
I'm sorry, I didn't understand how did you reach the multiplication?
Because here it is a vector. It's a set of weights. And the input is also a vector, a set of numbers.
Yeah.
This is in one neuron. One neuron has a set of weights, and they are of the same dimension. So we can compute the dot product. If this is a vector, this is a vector. We can compute the dot product by multiplying this by this plus this by this, and so on. This is one formula for the dot product. The second formula for the dot product, we can do it by f multiplied by s multiplied by cos alpha. If they are very close, these two vectors, if they are the same, it means they are superposed like that. Alpha will be what? Zero. Exactly, it will be 0. So the more closer they are, the higher the product. Yeah. The closer they are, the higher will be the product. So this is a distance measure, a dot product. A neuron can act like a distance measure, similarity measure. High values mean if the value is high, it means that these are similar. Low values means that they are dissimilar. That's why we can use what we call the max pooling, or sorry, not the max pooling, the ReLU. The ReLU, when it is positive, we keep it as it is. When it is negative, we remove it. We make it 0. It's because when it is negative, it can be like this, or it can be like this, it can be like this, and it doesn't really make sense. It's just so different from this. When it becomes 0, negative, it means just so different. It can be this or this or this or this, but they are so different. They are all too different. It doesn't really make sense if it is negative or 0 or so. So that's why in the ReLU, any negative value we can make it 0.
Actually, my question:
Sorry?
did you jump from? My question was, how did you jump from the HFS from the features to the multiplication? I didn't understand the relationship between the features.
The definition of the dot product and what we are doing in a neuron, one single neuron, what it is doing, a neuron, it is multiplying each input by a weight plus another input by another weight, and so on. Yes or no? So this is a sum, a WI, XI. So this is a vector, the WI. This is one vector. This is a second vector. The W, not WI. Yeah. The WI is one vector. The X is one vector. And what we are doing here is a dot product, because we are doing this. This is the formula of the dot product. Another formula of the dot product is also this. And you can see this is a distance measure. If the cosine is high, the value will be high. They will be superposed like this. If the cosine is if cosine 0 means 1, if the cosine 0 is negative or so, it means that the vectors are so different. They don't represent the same thing at all. Okay?
Yeah. Sorry,
we went a bit to something complicated, but it's good to mention it. You don't need to understand at this point everything, all of this. We just mean here that high values, but you need to understand high values here means that we are very close to this shape. Low values mean we are far. 0, it means that it's completely different. So if we take the maximum here, argmax, for example, here, this is position number 2, 0, 1, 2. It means this is class 2. If, for example, here it is 5, 0, 0, 1, it means here what we will have? What will we have here?
Class 0.
0.
Class
Perfect.
0.
So this is how this net, and then we get this map, a single map matrix that classifies every pixel. However, are you happy with this? Did you understand how we got the classes, even vaguely?
Yeah. Right.
Perfect. So one of the problems is that if we do this kind of neural net layers that have the same size without max pooling, because max pooling would reduce the dimension, and we lose the positions if we use max pooling. It reduces the dimensions and we lose the positions. So, but the input size will be huge, and with the number of weights will be just insane. So what we do the normal downsampling with the max pooling here, and then we do the reverse. There is a process that is the reverse of the max pooling. So we do like with the regular max pooling, convolutional layer max pooling here, 3 convolutional layer, then max pooling here, and we go to something that is very small. But after this, after encoding, after detecting these big shapes, we do the reverse thing. So the reverse thing we can use, we call it upsampling. We call it upsampling, like in here. So here, 1 becomes, we call it the nearest neighborhood. We just duplicate it. Bed of nails, we just put everything to 0 to make it bigger. This is a little bit like the reverse of the pooling. Sorry?
I'm sorry, but I don't see what we should gain when we do the reverse, because okay, I understand when we do the down
yeah. We need the matrix. We need the full matrix of things. So when we go like this down.
Yeah.
So we
lose some data actually, but we don't care because we are interested in the shape. So it's okay.
We still have the shapes. Yeah.
Yeah, but in the reverse side, what we will gain
is to go back to our full matrix. To go back to our matrix that will give us what do we have here? It will give us a class.
I see.
Okay, we do it little by little, because here we are reducing. We are getting here the bigger shapes. Everyone will be focusing on one zone of the image, and then when we go back, we get what it is. So,
but could you go back? Could you go back, please? No, the other one. I'm sorry. Here, instead of going back, why we don't just scale down the target image
to make it smaller, even?
Yeah, to make it smaller,
yeah, it's a problem. It's already 256 by 256, and if you go even down, you will lose some information even more. So we don't really want to do that. To go even to make it even smaller, we will lose certain things. For example, if you have something that is small in here, you already resized it to reach the target size, because we can't have big images here. And if you keep doing it, it will just be too much for the image. and you will lose small details. So we don't really want to do that. Here we are doing the downsampling to detect the bigger information, the bigger shapes, and then we reverse it to go back to the different like pixels.
Here,
we revert back to the pixels.
Honestly, if I would program it, I would prefer resizing the target image. Those is in the right.
If you can afford it.
What?
If you can afford resizing, because as I'm saying, the image is already very small. If you are using ResNet 250 something by 250 something like that.
But it doesn't make sense if you have to upsampling it to match it. Well, anyway.
No, you downsample to detect the bigger shapes. For example, this is a cow. We have here a cow. We have here grass, and things will overlap in here. There will be some problems.
Mm-hmm.
Like because things are we have multiple feature maps, and here we will have like grass, cow, and you will have multiple classes overlapping together.
Okay.
Pointing to the same region. So reversing the sample, upsampling will be able to disentangle them and to detect what this is really is. It's not that simple that we are just that all the information is already here. It's not really the case. We don't really have everything here.
Okay, I see.
Yeah. So we have these possibilities. We do the reverse pooling. You put everything at 0, or you just duplicate. You can also remember which element was max, for example, in here. To have it the same, you can see where did you do, what element you kept in the max pooling. For example, here, we went here, and then we want to reverse. So we remember here, the equivalent part of it, that 5 was the maximum. So we put the 1 here, this one, in here. And we put everything at 0. It's like we keep track of where the maximum was. Same for this and this, and same for this and this. Does it make sense for you guys, this? Is it clear here?
Yes,
yeah. Just you remember what was the maximum before, and when you do you do the reverse max pooling, you put it not like in here. We don't look at that. For example, we put it only on the corner, but in the other thing, we look which one we took before, and we put that one in its position where it came from. Here 5 will become a 1. So this is for the max pooling with some kind of memory. And then we have the more interesting part. I think I will have to stop here. It's too much. I will ask you to look for it, transpose convolution. It's a little bit, not really, but very close to like a reverse convolution, but it's not really the case. It's called transpose convolution. And we can really use it even for something like this. Transforming an image that is 480p, a small image, into a 4K. And if you have, for example, some sort of types of TVs that are very expensive, you can see that they can do that. They can transform like your signal HD to like 4K or even 8K now. And the result can be really impressive. Have you seen that, guys, before? Have you seen it?
You mean it will improve the quality of image?
Exactly, go into the higher resolution. For example, 480p to 4K, and the quality will still look good. Not like in the old types of super transformation. The super resolution aspect where we just took the average between the points that surround the pixel, or this kind of ways. This is like what we call interpolation. We used to call it interpolation in the time. Interpolation is something very rigid, but here with neural networks and with this kind of transpose convolution, you take like few pixels and you transform them to a higher number of pixels, like here. This was used mainly for this, to do this. A bit like reverse convolution, but it's not really the case. So I would ask you to look for it, transpose convolution, guys, for next time. Okay?
Okay.
Yes, thank you.
Thank you, guys, and sorry for, I know it's a lot of information at once. Remember, you don't need to understand everything, just like the main things, and you can build your understanding over and over. So thank you, and see you next time.
Thank you.